Welcome. We conclude our chapter on cyclic groups and talk a little bit about generators of cyclic groups, and then we are going to write down the automorphism group of a cyclic group of order n explicitly. So in here it's convenient to use a function from elementary number theory, Euler's phi-function. And phi simply counts for any number n that is a natural number, the numbers between 1 and n that are co-prime with n, meaning the numbers that have no common divisors with n. Or in other words, where the greatest common divisor is 1, because then there is no common divisor except for 1, of course. So phi of n is defined to be the cardinality of this set here, the set of all natural numbers between 1 and n. We could also write this here if n is not 1, because then n and n clearly have n as the greatest common divisor. So all the numbers between 1 and n that have 1 as a greatest common divisor. So remember, this was an abbreviation for the GCD of two numbers, simply those round brackets. So for example, if we take n to be the number 15, then which numbers satisfy these conditions here? Of course 1. 1 is always in this set. Then 2 is co-prime with 15, 4 is co-prime with 15, 3 not, because 15 is 3 times 5, 5 not, again because of this factorization. 6 is not co-prime because 3 is the greatest common divisor of 6 and 15. Then we have 7, 8, 9 not because of the 3, 10 not because of the 5, then 11, 12 is not in here because of the 3, 13, 14, and of course 15 itself not. So this set here has 8 elements, so phi of 15 is 8. Then here's some more properties of the phi function that are very useful in number theory, elementary number theory. We won't be needing them, so they're just recorded here for sake of completeness, but I'm not going to talk about them in depth. Maybe just this here, the Euler phi function of a prime number clearly is p minus 1. Because all the numbers from 1 to p minus 1 have no common divisors with p. Otherwise, p would not be a prime. Okay, so what is of interest to us here? We assume that G is cyclic with generator x. Then there are two cases. If the order of x is infinite, so G is an infinite cyclic group, then x and its inverse are the only possible generators of G. So x generates G by definition, then also x inverse generates G, and that's it. There can be no more generators. And if you have proposition 32 in mind, you remember that in this case G is isomorphic to the integers. And the integers, of course, have only two generators, namely 1 and minus 1. This is essentially the proof for this statement that we are going to look at in a minute. Now comes the interesting case. If the order of x is a finite natural number n, then G has exactly phi of n distinct generators. And they can be written down explicitly. They are all the powers x to the k, x being the generator, such that k and n have greatest common divisor 1, so they are co-prime. And of course k runs between 1 and n. So for example, a cyclic group of order 15, which would be isomorphic to z sub 15, the integers mod 15, will have exactly 8 generators, namely x itself, x squared, x to the 4th power, x to the 7th power, and so on. All these powers of x will generate z sub 15 or any cyclic group of order 15. Okay, let's take a look at the proof. As I've just mentioned before, in the first case G is isomorphic to the integers via the homomorphism going from z to g. An integer k is mapped to x to the k. This is what we used in proposition 32 of the proof thereof. Now, it's a general fact that an isomorphism always maps generators to generators. This would be a neat little exercise for you to prove for yourself. And clearly, 1 and minus 1 are the only possible generators of the integers, because all the subgroups of the integers have this form. So the cyclic subgroups generated by integer d, and clearly all of z can only be achieved if this here is plus minus 1. Otherwise, there will be numbers missing. But this means, because phi sub x is an isomorphism, that exactly these powers of x are the only generators of g. So x to the plus 1 being x itself, or x to the minus 1, so the inverse of x, are the only possible generators of the group G, and this is it. Okay, so by definition, if x is a generator of G, G consists of all the powers x to the m running through all the integers, but since x has the order n, this set here consists exactly of the identity being x to the 0, x itself, x squared, and so on up to x to the n minus 1, which is exactly what is written here. Or if you prefer that, you could write m runs between 1 and n being included, where x to the n again is the identity. This is the same. So which powers of x are actually generators? So for which x to the k is the generated subgroup by this element the same as the group G itself being generated by x? Well, clearly if and only if the order of this element is n, because this is a subgroup of this, and they can only be equal if they have the same order. So the order of this subgroup is exactly the order of the generator, so this needs to be n. But from proposition 30 we know that the order of x to the k is the order of x, n, divided by the GCD of n and k. So clearly, if and only if the GCD of these numbers is 1, this has order n and generates the whole group, and this is already it. And then we use the convenient notation that there are exactly phi of n here, phi of n elements that satisfy this condition. Okay, to conclude our chapter on cyclic groups, we make the following observation. For cyclic groups, it is possible to write down the automorphism group explicitly. And this in general is very, very hard for an arbitrary group, but for cyclic groups, it is, well, not easy, but it can be done nicely. So, remember what are the automorphisms? Now I write z sub n for a cyclic group of order n. I make a distinction here because we know that in the end this will be isomorphic to z with a double line sub n, so the integers mod nz, but this group has another meaning in this context, so I prefer to write z sub n without the double line as the general cyclic group of order n, without using the isomorphism to this group here. So, an automorphism is a homomorphism from the group to itself that is an isomorphism. So all the bijective maps from the group to itself that are homomorphisms build the automorphism group. And to characterize this, we will need the so-called group of units of this group here. This is, if you know the term, actually a ring. We can also multiply these residue classes, not only add them, which gives me the group structure, but I can multiply them. So, I take a residue class, a bar, mod n, and I call an element a unit of this ring here, denoted by that, this here with a star, if its inverse exists, but not the inverse with respect to addition. Clearly this always exists because this is a group with respect to addition, but with respect to multiplication. So let's take a closer look at this. We already know that if here is a plus sign and here, this is the well-defined addition that makes Z mod nz into an abelian group. But instead of adding residue classes, I can also multiply them. So I define A bar times B bar to be A times B and then bar. So then taking the residue class mod n. And as always, when working with residue classes, you need to convince yourself that this is well defined, so that it does not depend on the choice of representative. Because in general, there are many possible choices for A and B. But I choose one representative here, A, and one representative here, B. And this must not depend on the choice of representative. Otherwise, it's not well defined. We're omitting that here. That also would be a nice little exercise for yourself to check that this is a well-defined multiplication. And here, the identity clearly is 1 bar, because if I have 1 bar here, I end up with 1 times B and then residue class, so nothing changes. So 1 bar times B bar becomes B bar. So clearly 1 bar is the identity, but this in general is not a group. Well, of course, it cannot be a group because it contains 0 bar, and for 0 bar, I cannot find an inverse with respect to this multiplication, because 0 bar times B bar is always 0 bar, so I cannot end up with 1 bar. So it's not possible that this becomes a group, but together with plus and this multiplication, it becomes a so-called ring. But if I take this condition here, if I take all the residue classes that have an inverse with respect to this multiplication, it is easy to check that this indeed is an abelian group. And with this so-called group of units, we are going to work. Okay, now here is the important observation. We take a residue class in this group of units. Then by definition, this means there is another residue class, B bar, such that this here is satisfied. This exactly means that A bar has B bar as its inverse, because this is clearly commutative. I do not need to check left or right inverse, or as you remember, we showed that left inverse is, doesn't matter. So clearly, this means such a B bar must exist. Now, we remember, what does it mean that two residue classes are the same? This means there is a number B such that AB is congruent to 1 mod n, and this is the same as saying that AB minus 1 lies in nz, so that AB minus 1 is an integer multiple of n. If you understood residue classes back then, this should be clear. Okay, but this by definition means there is an integer m such that AB minus 1 can be written as n times n. N times m. Oh, okay, I just realized I made a mistake here. I had a wrong sign. I bring this to the right side of the equation with plus 1, and then here I have minus n times m. But that can be easily fixed, because this here can be written as AB plus minus m times n. And if m is an integer, clearly minus m also is. So, and here I could write b times a. So what we have here is a so-called z linear combination of a and n, because here the coefficients b and minus m are integers. So this is an integer linear combination of the numbers a and n. And if this is 1, then the very important lemma of Bézout, or Bézout's lemma from elementary number theory, states that this is the case if and only if a and n are coprime, so the GCD is 1. We're not going to prove that here, but in elementary number theory you will learn that lemma of Bézout, very important lemma. So if and only if this integer linear combination gives 1, then a and n are coprime. So to summarize this, we end up with the following important observation. A residue class A bar lies in the group of units of Z mod nz if and only if A and n are coprime. This will be a very important observation for our next proposition. Okay, and now we are in a position to be able to state the main result. Proposition 34. Let's assume Z sub n is the cyclic group of order n, because up to isomorphism there is only one. Then its automorphism group is isomorphic to the group of units of Z mod nz. And these are exactly the residue classes that have greatest common divisor 1 with the number n, or that are coprime to n. This is what we just understood here. So the automorphism group of a cyclic group itself is abelian. This is not clear because automorphisms need not commute. And the order is exactly phi of n, because by definition of Euler's phi function, there are exactly phi of n numbers A that satisfy this condition, between 1 and n, of course. Okay, so to stress that again, in general it's very complicated to get a grasp on the automorphism group of an arbitrary group, but in the case of a cyclic group, I can explicitly write it down. All right, my time for this week is up. This video is too long already, and the proof will require some work that we will do step by step in next week's video. Thanks for watching, and I'll see you next week, hopefully. Bye-bye.